Okay, let's get started with lecture 13, which is about combinatorics, and combinatorics is all about counting. We'll start by finishing off the domino problem from last lecture, and here we have a set of 28 domino tiles. Domino tiles have numbers on each side of the tile. So, for example, 6 and 6, or 0 and 0, 3 and 0, and they could, of course, be rotated as well. So you could have something which is a functionally equivalent like that. So our friend picks a random tile from the set and tells you that at least one of the sides is a 6. What is the probability that your friend's tile is a double with 6 on both sides? So in this case, it's important to write or look at what the question's asking. So friend picks a random tile from the set and tells you that at least one of the sides is a 6. So already we know that we're dealing with a domino tile where at least one of the sides, so that side or that side, has a 6. So I guess actually it could be this. So that leaves us with only 1, 2, 3, 4, 5, 6, 7. So our space was S equals 28, but at least one side has a 6. So now we know that our S actually equals 7, and it only equals these ones right here. So this is the new space, probability space that we care about. And particularly, we want to know if one of these, what is the probability that your friend's tile is a double? So particularly, we're only interested in this outcome, where it's both a 6 and a 6. So that's this outcome right here. So this is just simply the probability that we have a double given at least one side equals 6. So that's going to be the number of doubles with at least 1 6 over the number at least with 1 6. So that's going to give us 1/7 is the answer, because our probability space has turned into just these 7, and we only care about the outcome where there's a double 6. So easy question at the end, but important to know this idea right here, which we get from this part. Okay, question 2. So we now pick a random tile from the set and uncover only one side. So we have a tile, and we have some number here, but we cover up this side. So this is our big unknown. We'll pick a random tile from the set, uncover only one side, revealing that it has 6 dots. What is the probability that this tile is a double with 6 on both sides? So in this case, we have tiles that we're picking, and we have both sides that we could see, but we're only revealing one side. So already we're not dealing with a probability space anymore of 28. We're dealing with a much smaller probability space. In actuality, we're dealing with, maybe we'll use blue, we're dealing with this, and this, and this, and that, so on, and so forth. So we now have 1, 2, 3, 4, 5, 6, 7, and 8 sides that are revealed. And this is a special case because this is one tile, but two sides. So we have 28 dominoes. We have 28 dominoes, and we have 56, so 28 times 2. So 56 sides. And of the 8 half dominoes that are equal to 6, only 2 are across from another 6. So, right, what is the probability that this tile is a double? So of the 8 half tiles, only 2 are across from a 6, namely these two right here. If you reveal this one, it's across from a 0. No, you reveal this one, or this one, or this one, or this one, or this one. All the ones that are across from it are not a 6. But if you reveal this one, it is across from a 6. And if you reveal this one, it is also across from a 6. So it's just 7 and 8 here from our set of domino halves that could work. So this becomes actually a very easy problem to solve with those considerations. It is the probability of a double given uncovered 6. So this is just 2 over 8 or 1/4, because we have 1, 2, 3, 4, 5, 6, 7, 8. That's now our new probability space. And only these two are going to be a double that's across, fulfills this requirement, which I will also highlight. Okay, so that's the important one, and a really great thing to get in the habit of, if you're trying to, especially in like the homework, is when you're trying to solve these probability problems. Doing it this way is good, but you can also just as easily create, like using NumPy in a Jupyter notebook, you can create little probability kind of examples where you can continue to run trials over and over again and see what the probability would be. So you could create these dominoes and run trials and see that you'll get this answer of 1/4, which we have right here. So the probability of a double 6s, given that we uncovered a single side and it was a 6, gives us 0.2514, and that's done over many, many trials. This is just the other two from the other example, and then this one was the example from last lecture where it was just the simple 1/4. Okay, so those just to round off the domino example from last week, or from last lecture, and now we'll go ahead and start to kind of dive into combinatorics. The whole idea behind combinatorics is that we have to have some way of expressing how we count things. And probably, most, not most, but certainly many problems in probability involve counting, flipping a coin and trying to see, how many heads can you get is a form of counting. Drawing decks from a card and seeing if they're all from the same suit is a form of counting outcomes. And through counting those outcomes and how we choose to count things really has a lot to say with how we derive and calculate these probabilities. So just to make it explicit, combinatorics is all about one, counting, or how we count, and also from those two statements, accounting and how we count, really it's the number of ways we can do something, if we want to generalize it. And learning how to count, what we mean by that is we first need to learn how to count means that counting 1, 2, 3, 4, so on and so forth is one form of counting. But if we're counting, let's say, the number of cards from a deck, if we draw a card and count it, do we then take that card and replace it or throw it away? So there's lots of things that come into play here that we'll see. Specifically, this is what's called replacement or non-replacement. Does order matter or not matter? And when we're doing experiment, what we're really probability experiments, what we're really doing is trying to, you can say, like selecting so selecting k items. Let's put from n possibilities. And that's really important. When we have probabilistic experiments, we choose these k items or elements from a group, and that group is called a population. So this is where we kind of like dovetail back into thinking about how probability leads us to doing proper statistical analysis. For example, like if we have a deck of cards, the deck is the population and the cards that we draw from it is our sampling. Or all the students who take DSC40A, like let's say that I was teaching 3 sections of it and there was 100 students in each section, all 300 students could be said to be a population of the DSC40A students. DSC40A students, section A, that population would be just like the 100 students. And when we're counting or sampling from a population, we also have a very important consideration to make, and this is, do we order or does order matter? And then do we replace? And that example would be, you have some sort of for replacement, you have some sort of deck of cards here. So this is our deck of cards, and we could say, are they ordered or not? That's a question that we have. And then the next question is, if we were to draw a card, so draw a card, and we'll put an exclamation mark for spontaneity. And that card winds up being, the ace of diamonds. And, ace, that's a nice card. Do we then take that ace and do we replace? So this is, a deck has 52 cards. And do we replace it back into the deck so that it maintains 52 cards still? And then how do we put it back on top? At the bottom, we reshuffle it in. Or do we throw away the card? And by throw away, I don't mean, necessarily like throw it into a waste bin, like the trash. We mean, do you put it off to the side such that your deck of cards would only be 51 cards now. So that's what we mean by replacement versus not replacement. So this is the considerations that we need to make. Especially these are the considerations that we need to make when we're doing selecting elements or counting from a population. So this is what we will be talking about in this lecture, and we'll start with sequences. So let's talk about sequences. A sequence of length k is obtained by selecting k elements from a group of n with possible elements with replacement, so repetition is allowed, and such that order matters. So we're allowed to, for example, drawing a card from a deck, we're allowed to draw a card, see what it is, and then put that card back in the deck. So we could draw the same card again. Let's go ahead and do this one then. So if we have n equals 52, we'll do purple. And here k equals 4, right? Because we have n possible elements. So a deck of cards has 52 possible cards or 52 possible elements. And a sequence of length k is obtained by selecting k elements. Well, we're going to select 4 cards because we want to repeat this 4 times. And we have we're drawing a card from a 52 card deck and put it back, right? So this tells us replacement, 52 cards is our n, repeat 4 times, that's our k, and drawing a card, okay. So how do we actually write this out? Well, we have, it's oftentimes a good strategy to kind of like draw a pretty picture. And by drawing a pretty picture, we're going to have a slot where we draw our first card, and then our second card, and then our third card, and then our fourth card. And every single time we draw a card, we will take that card and replace it. And then we'll replace it. And then we will replace it. So what does that tell us? Well, that tells us that every single time we draw a card, we put it back, thus the deck never goes below 52 cards. So we have 52 cards, 52 cards, 52 cards, and finally 52 cards. So thus our sequence is 52 to the 4th possible sequences. So that's how many different options we have essentially for the 4 cards we could draw. So 52 to the 4th. All right, UCSD PIDs start with A, then it has 8 digits. How many PIDs are possible? All right, so we have 8 digits, always starts with an A, and then how many are possible? Actually, I need to highlight that part. We know that this is with replacement because it has 8 digits, and you can have repeating digits, right? You can have a 1 and then a 1, so on and so forth. So let's start with N and K and figure out what those are. So we know that we're going to have a digit that we could choose for every slot in our number. And we know that digits range from 0 to 9, so there are 10. And we know that it has 8 digits, so we're going to have 8 things that we're kind of creating. So here we have our fixed A, so this doesn't change. And then we have our slots for number 1, and then number 2, and then 3, 4, 5, 6, 7, 8, 9, and then 10. And what this tells us, so we'll say, I don't know, maybe we have 8, then 7, so on and so forth, and then 1. It doesn't matter. But what this tells us is that, I'll do this in purple again, is that we have 10 times 10, blah, 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 times 10, and we do this 8 times because our K is 8, so there's 8 elements from our group. So this is just going to be 10 to the 8th. Okay. So is there a kind of general idea from sequences that we're able to kind of extract from this so far? Well, we've kind of been following this idea that we have a first element, and then we have a second element, and then we have some kth element. Why kth element? Because if you look here, we have k equals 4, 4 things. K equals 8, 8 things. Remember, k elements. So our deck of cards is an element, and we're going to draw from that deck of card 4 times. And each time we're going to replace it. We're going to pick 8 random digits from 0 to 9. So we're going to do it 8 times. So that's where the idea of k comes from, the kth element. And it's important to note as well that this is the k minus 1 element. So this winds up also having us put n up here, because we have n possible elements that we can draw from. So again, we have 4 elements, the deck of cards, and then from each element, we're selecting n possible items from that. So 52, because we have a deck of cards that are 52. So the generalization of this winds up looking like n times n times n over k times. So this gives us n, not over k times. What am I thinking? This occurs k times. So we have n to the k. It's important to realize that we have this formula, but I still will argue the idea that drawing the pretty picture, right? Like, we have these formulas that we can think of, but sometimes it's hard to know exactly what goes in here or how you write this. And sometimes drawing the pretty picture, right, like writing this out explicitly, can help you sort through the logic of what you're doing. I think that can be very helpful. Okay. Permutations. So permutations are a lot like sequences. In the case now we have without replacement. So we're still selecting k elements from a group of possible, you have n possible elements, but we no longer have, without replacement. Order still matters, but without replacement. And that's the main idea about permutations. So let's try redoing these same kind of similar examples. So here we still have n equals 52 and k equals 4, because we're drawing 4 cards from a standard 52 card deck. However, we are no longer doing it with replacement. We're doing it without replacement. So once you draw a card, the Heart of Kings, that Heart of Kings is removed from the deck and it can no longer ever be drawn again. So in this example, we still have our K elements. So here's the first one, and here's the second, third, and fourth. But now we start with 52 cards, and then we say, okay, one card goes away, so this becomes 51 cards. And why is that? Well, because these 51 cards can be, okay, let me write it down. These 51 cards can be any card except the first K card, which is the card over here that was selected. So third one, similar vein, 50, and then 49. Maybe we'll put K card in quotes, keep everybody happy. So what does this give us? This gives us 52 times 51 times 50 times 49. Okay. Now for this one, how many ways are there to select a president, vice president, and secretary from a group of 8 people? So in this one, we're going to write down our n and k again. That's important. So in this case, n equals 8 because we have 8 people. K equals 3 because we're selecting for 3 positions, right? Group of 8 people, selecting a president, vice president, and secretary. So let's start with drawing our 3 things. So we know we're going to have 3 items that we select. And this is going to be, let's just start with president, vice president, and secretary. So if we've got 8 people, then if we're selecting president, there are 8 people that we could select from for president. And just like when the cards were at 51, those 51 cards could have been anything except the first K card. Well, now your VP could be any of 7 people. The only person it can't be was the first person that was selected for president. And same thing for secretary. And so this just gives us a very simple answer of 8 times 7 times 6, which equals, let's see, 8 times 7 is 56. Then 50 times 6 is 300. 6 times 5, 36. So 336, yeah, 336. Or, yeah. Let me just double check. Let's see. 8 times 6, yeah, 336. Yeah. 6 times 5 is 35, 36. Okay. So let's see, let's move on to the next example. So this would be sort of like we want to come up with a general understanding of what a permutation is. So let's see. First thing is, let's define this because this is going to get confusing. So here P equals a permutation, not probability. So that's the first thing to get. Okay, so we have the permutation of nk, and that equals n times n minus 1 all the way until n minus k plus 1. And the definition of n factorial, because that's a good place to start with this, maybe we'll do it in yellow, is n factorial equals n, so some number, times n minus 1 times, let's say, 2 times 1. So assuming that n is some number larger than 2 here. So for example, one way to think about this might be, let's say we have some large number like 100 factorial, and that's going to equal 100 times 99 factorial. And that's going to be the same thing as saying 100 times 99 times 98 factorial, which is the same thing as 100 times 99 times 98 times 97 factorial, all the way until we have 100 times 99 times times 2 factorial, or 2 times 1. So what is the point of this? Well, we can express the factorial in this case as being some large number or some number, and that number can be expressed as a bunch of other numbers being multiplied until you get to some bottom number. So in this case, like 2 or 1. So we'll use that idea to show how this factorial can be written. Okay, so permutation of n k equal to n factorial over n minus k factorial. Now, why is this so? Well, we can rewrite n factorial as being, and think about what we did over here, we can rewrite it as n times n minus 1. So this would be like 100 times 99, then times some other stuff, times, we could say, n minus k plus 1 times n minus k factorial. So we're kind of making use of what we did here over here to describe what is going on here. And we can say that's all over n minus k factorial, which we get from down here. So we've taken this n minus k factorial in the denominator and brought it over. And then we've just taken this n factorial and expanded it out into this. And we did that because we know that n factorial is just some number n, and you can describe all these intermediary parts of it, which is the next number in the sequence, and then some number in the sequence minus k, plus 1 until you get to some number in the sequence minus k, which would be the end. So if we do that, then we can cancel that out, and we're just left with n times n minus 1 times n minus k plus 1. And this looks a lot like purple. This looks a lot like what we have up there. So here's a generalized expression that we can use for these permutations now, n factorial over n minus k factorial. And you can go ahead and plug these, using these equations, plug this stuff in, and you'll see that it does work. For example, the card case, it would be n equals 52, and then you have n minus k plus 1 would equal 52 minus 4, which is our k, plus 1, which would then equal 52 minus 3, which would then equal 49. And that would be the same expression that we had before, represented like this. So I encourage you to go and try plugging it in and see if they work. Okay, so let's try doing a question. UCSD has 8 colleges. In how many ways can I rank my top 3 choices? So let you have a few minutes and think about that. Okay. Well, if we have 24, that's just 8 times 3, and 512 is just 8 to the third, and 6,561 is just 3 to the 8th. So we've got 8 colleges and your top 3 choices. So your 8 colleges is going to be something that's a lot like your n, and the number of colleges that you have, your top 3 that you're trying to rank, is a lot like your k. So let's just try and use those values. So we have n equals 8, k equals 3 here. So we know we have 3 options. So your first choice, second, and third. And your first choice is going to be one of the 8 colleges that you choose. Once you choose one, you only have 7 to choose from, and then 6. And so this is just going to be 8 factorial over 5 factorial, which makes sense because if you have 8 factorial and 5 factorial and you cancel things out, what you will get is just 8 times 7 times 6. And what I want you to see here, though, is that even though we could have just used this equation, writing down these things can help to identify the logic and figuring out what these are, rather than straight going for something like this. So keep those in mind, and we'll go ahead and talk about special cases of permutations. Let's look at the special case of permutations where we have n people, and the total number of ways I can rearrange these n people in a straight line is. So to solve this, we're considering that in this case k equals n. So here our k equals n. So what does that mean exactly? Well, we still have our pre-picture that we can draw, where we have a first person, and then we have a second person, and a third person, and so on and so forth, until we get to n minus 1th person, and finally our nth person. And when we think about what we can actually choose from, and remember, if we're thinking back to these examples, for example, with the deck of cards, where we have 4 draws we're going to take, and we have 52 deck of cards, and we start and draw from it. Here we have n number of people, and we're going to rearrange them. So we would have up here n minus 1, n minus 2, all the way until we get to 2 and 1. So this is really telling us that we have n times n minus 1 until we have 2 times 1. And what is this? We just saw this. Where do we see this? We just saw this back over here. N factorial. So n factorial is what happens when we have k equals n. And it's consistent with the formula right here with the permutation of n and n, as k equals n. So we just replace k with n in there. And one thing that's interesting to note here is what's happening over here. Well, 0 factorial is, believe it or not 0. It is 1. So if it was 0, then of course this wouldn't work out. You divide by 0. You can't divide by 0. So here we have n factorial over n minus n factorial, because we just replaced n with k. N minus n is 0, but 0 factorial is 1. So n factorial over 1 is just equal to n factorial. So this is how we deal with these special cases of permutations. Here's an example, like an interesting question. How many ways are there to arrange n people in a circle? So you might be getting some idea here for what's going on, but let's just write it out. Let's assume we have people A, B, C, and D. And let's say that they are A, B, C, and D. So what's an operation that we can take? Well, we can rotate one place. And so what happens when we do that? We now have D, A, B, and C. And we can rotate again and again so that we have C, D, A, B, and then we have B, C, D, A. And functionally, these are all equivalent. Because there's no idea of a starting point here, there's just a circle that we're rearranging people in. So the number of arrangements are 4 factorial over 4, which just equals 3 factorial. And the general case here is n minus 1 factorial. So where n equals 4, we can think about the general idea of n minus 1 factorial. Let's see. In fact, we can also think about this problem in a little bit more of a interesting way. Maybe we'll do it up here. So let's just write some more stuff over here about circles. We'll call this the circle problem. So instead of rotating people around, let's assume that we've have a person who's a fixed person, and let's say that maybe we'll just draw it out here. We have some sort of table with n seats, and there's whatever seats. There's one special seat though, and that's a seat at the head of this circular table. Think of King Arthur and the Knights of the Round Table or whatever. So this is the head of the table. So this is a fixed person. And we can draw this even a little bit better. So we have our head of our table, and then we have n minus 1, n minus 2, n minus 3, until we get finally into 2 and 1. So these are all, this is our table. We have 1 seat, 2 seat, 3 seat, 4 seat, 5 seat, 6 seat. But again, the seats are n number of seats, so it's arbitrary. And let me actually move that a little bit. Okay. So how many different arrangements are there? Well, we have a fixed person in place, and we can take simply n minus 1 times n minus 2 all the way until we get 2 times 1. And what is this? Well, this is just n minus 1 factorial. And n minus 1 factorial can be expressed as n factorial over n. And that's how many rotations we can make for this problem with a fixed person at the head of the table. Because just like the deck of cards, we select one person to sit at the head, and that's done. And then from there, we can select from the remaining people a person to sit in that chair, and we can do this over and over again. All right, let's talk about combinations. So a combination is a set of k elements that are selected from n possible elements without replacement. The big difference here than permutations is that order does not matter. So we don't really care about order. We just care about all the possible combinations of something, which means that we're going to run into issues of perhaps double counting. So we'll see what that looks like in this ice cream example. So let's assume we have our 4 ice cream flavors, and you always have to have vanilla, and you always have to have, why not, chocolate, and strawberry is another famous flavor. And let's also go with taro. Why? Because taro is good. Why not? Okay, so these are our 4 flavors. So we have our 4 ice cream flavors. And how many ways can you pick 2 different flavors? How many ways pick 2 different flavors? So this is small enough that we can actually enumerate the entire probability space. So we can assume that we have vanilla, chocolate. We can assume that we have vanilla strawberry and vanilla taro. And then we can also get chocolate strawberry. And then we can also get chocolate taro. And we can also get strawberry taro. So here are 6 combinations. Again, we have 6 because strawberry taro is the same thing as taro strawberry. So we wouldn't write like this, right? This is the same exact thing. Remember the dominoes? Yeah, we're kind of writing we have this triangle, and we don't need this bottom triangle because they're just always these flavors over again, but just flipped. So we have 6 combinations. Now, why isn't it 12 combinations? Again, because we're not want to double count, but if we considered, if we thought about this problem typically, where order does matter, we might be inclined to say, and this just to round out this idea, that we have 2 flavors. So we have the first flavor, and we have the second flavor, and for the first flavor, we have 4 possible options, and in the second flavor, we would have just 3 possible options. And we might say like, okay, easy. This is just 4 times 3, which gives us 12. And while that's kind of close, we would be double counting basically all the flavors that we didn't list, which would be, well, includes this TS one, but it would be these ones here. So this is flavor combos, and this is not it because of double counting. Okay. So let's actually assume we live in a world where we don't get 2 flavors, we get 3 flavors. Why? Because 3 flavors means 3 times the fun. So if we can select 3 flavors, let me just write the setup here. Of course, you get a smiley face because it's 3 flavors. And you have to have a waffle cone too. You get your 3 flavors of ice cream. So everyone's happy. Okay, so we have our 3 flavors from our set of 4 possible flavors. So what are we gonna do? Well, let's think about one combination. Oops. Let's look at chocolate, vanilla, taro. So for one combination, there are 3 factorial ways of rearranging these flavors. And let's be clear, they're all the same combination. So in this case, we would have chocolate, vanilla, taro. We would have chocolate, taro, vanilla. We would have vanilla, taro, chocolate, vanilla, chocolate, taro. And taro needs to be first now, so taro, chocolate, vanilla, and then taro, vanilla, chocolate. All right, so these are our possible combinations, and they're all the same. So this is like saying that we have let's see, 3 factorial, so that'd be dividing 24 by 3 factorial. And this allows us to get all the possible combinations because we have 24 total permutations that we could select from the ice cream. So this would be 4, 3, and 2 because we have 4 possible flavors. This is the first flavor, second, and third. So this equals 24 because 4 times 3 times 2, so 24 permutations of scoops. And that's going to be divided by 3 factorial. This would be combinations, just right up there. So this would be 24 over 3 factorial 6, which equals 4 combos. So the solution here was to divide the 24 possible permutations that we could have gotten by 3 factorial, which was an adjustment for the repeated permutations that we saw. So these are the possible repeats. These 1, 2, 3, 4, 5, 6. Let's look at this idea of how permutations and combinations are very closely connected. So, for example, both of them happen without replacement. So that's important. And as far as permutations is concerned, permutations order does matter. So I'll just put and for combinations, order does not matter. And if we look at the this equation for combinations, we see one really important thing, and that's that the number of permutations is at the top, and that's n factorial. And if we remember, n factorial is it's the permutation, but more importantly, it's the permutation of distinct n or n distinct items. And that's really important. And we're going to have that over the number orderings of k elements. And now where does that come from? Well, that's this n minus k factorial. So that's this n minus k factorial, which is, from a permutations point of view, the permutation of n items taken k times. So that's the n items taken k times. Or that's to say also it's the number of ways to arrange k items out of a total of n items. And so that kind of gives us this part here, well, that part there, the factorial. But for combinations, we also have this adjustment here. So if we know that permutations, maybe better just to highlight, is this part, then we have this k factorial here. Where does that come from? So that's the ordering of k elements. Now, what does that mean exactly? Well, let's first start by highlighting it. There. So what that is, maybe I'll just put down this little adjustment here. We'll do it in blue. So this is an adjustment, and this adjustment is really, its main purpose is to account for any double counting. So let's put that. And we'll see some examples of that in a few of the examples that we're going to do in the rest of this lecture. But that's mostly, that's the main reason why it's there. So this is kind of the closely connectedness that permutations and combinations has. It's just with combinations, we care about that adjustment so that we don't have any double counting. Now, in combinations, I guess one first thing to keep in mind is we have a symbol here. That's not a division sign. So if you see, I'll do this in yellow, if you see n and k like this, it is not n divided by k. Rather, it is n choose k. That is the correct vernacular or nomenclature to use. And in general, what combinations is telling us is just the number of ways to select k elements from a group of n items, and that's without replacement. And so we have no duplicates. And in this case, order is irrelevant. And that's a real important distinction to, or important thing to keep in mind, is that we don't care about order. And if you've taken, probably, I think this might have been in Math 183, or if you're going to take Math 183, that's where you'll come across this again. And the n choose k comes from the binomial coefficient, which is just a way of kind of parsing out or expanding the a plus b to the nth or to the n equation. But anyways, it's not important. I guess an expansion of the sum of a plus b to the n. But I need to worry about that. So this is the definition of combinations. It's just this equation right here. And we have the parts from permutation, and specifically this whole thing is from permutations, and then the ordering of k elements, this adjustment factor for the duplicates. Okay, let's work through a really brief example. How many ways are there to select a president, vice president, secretary from a group of 8 people? Now, a thing to consider here is a difference between approaching this problem from permutations and from combinations. So from permutations, and this is, the way to think about this is to not even consider or think about the equations just yet. Like don't think about this stuff at all. Think about what the question's asking, and we'll start from there. So if we're going to do this with permutations, and that's how we're kind of thinking about it, in the case where we have a president, vice president, and a secretary. So that would be, how do I write that? President, vice president, and secretary. And let's assume this is, I'm going to run out of space. Let's restart that. So let's assume we have 3 people. Actually, I'll put this in the middle. We'll just reuse it for both. Okay. Yeah, let's assume for sake of argument. And let's assume those same people I'm going to run out of room again. Okay, we'll just use their first name, their first letter. So let's say that we have 3 people. In this case, president, vice president, and secretary. And for combinations, we'll assume the same thing: president, vice president, and secretary. Now, let's assume we reorder these people. So let's go. And now we have, again, the president, vice president, secretary, and the president. So looking at this from a permutations point of view, we've reshuffled the people, and we would say that these are not equal. That is to say, these are certainly the same people, but they've been reordered, and now we have people who have different positions. So in that case, that's fine. Now with combinations, these 2 things would actually be equivalent because the roles don't matter. Why don't the roles matter? Because we can assume role is sort of the same thing as an order, and orders don't matter for combinations. So in this case, roles So in this case, it doesn't matter what their roles are. Since it's the same 3 people, it is effectively the same thing. So if we had let's just do the math. And here we have 8, 7, and 6. So we've got 8 people. And this would be like saying the president, vice president and secretary. And that would give us 8 times 7 times 6, which would be 336. Okay. So now I ask, how many ways are there to select a committee of 3 people from a group of 8 people? So in that case, we would now write this as 336 over 3 factorial, which would be equal to 8, choose 3. So, we want to think about what that would look like if we were to, if you're trying to think about permutations versus combinations, this example is really nice because you can think about something like roles, which is a real world, it's analogous to a real world thing. In this case, would it matter if somebody's roles were counted or not? Or effectively, is it can be the same thing as long as the 3 people were chosen are the same? Because in this case, we had 3 people, and those 3 people were chosen again, and they're counted as the same thing because their roles don't matter. So in this sense, combinations are taking care of the duplicates because these 3 people are in fact duplicate. From a permutations point of view, they're not because they have different roles. J was a president and now J is secretary. And now A is president, where before A was vice president. So it is still the same 3 people, but their roles, or perhaps their ordering, has changed. So this is a good way to think about the idea of permutations versus combinations, and to really think about where this K comes from. Okay, so how do we simplify a N choose K or combination problem? Well, let's go through and do a little example. You can plug these things into your calculator or your computer or whatnot, but often, and this is a really good strategy to have for, or to remember this for like your exams. If we have something like, this one, 16, choose 3. Well, what does that mean if we plug it into the formula? We have 16 factorial over 3 factorial and 13 factorial. So let's go ahead and think about this. If we have 16 factorial, that's like saying we have 16 times 15 times 14 times 13 factorial. And this is now over 3 factorial and 13 factorial. So the 13s, or the 13 factorials, can cancel. And also because I guess I kind of wrote these backwards. It's throwing me off. 13 factorial, 3 factorial. We get this from n minus k, which is 16 minus, minus 3, which equals 13, and then k, which was 3. So that's where these two came from. Okay. So we know that we have the 13 factorials cancel out. So that leaves us with 16 times 15 times 14 over 3 times 2. or times 1, but whatever, 3 times 2. Why 3 times 2? Well, because we can easily reduce the 16 to the 15. So we can say this becomes 8, this becomes 3, and these go away, leaving us with a very nice 8 times, oops, that's incorrect, should be a 5. 15 and 3, yes, 5. So that's 8 times 5 times 14. So this is 40 times 10, 400. 40 times 4, 160. So 560. Okay, so yes, probably would have been faster to do this in a calculator. But no, in an exam, you might get stuff that's kind of like this. You're like, oh, geez, how do I work with this? But just remember that you can expand out some of the factorials to match other factorials, and those cross out. I mean, that's really the big one from here. This is just a slight simplification, but this was the big one to take away from here. Okay, let's go ahead and think about this problem. A domino consists of 2 faces, each with anywhere between 0 and 6 dots. A set of dominoes consists of every possible combination of dots on each face. How many dominoes are in a set of dominoes? So I'll give you guys a second to work on this, and then we'll solve it. Okay, so right off the bat, because this is running pretty long already, we'll just go ahead, and D is kind of meaningless, and C is definitely not the correct answer. So I think most people would probably just guess 7 choose 2, and they would probably guess that because you just use the equation that you've been given, and you go off to the races. Now, that's not necessarily a bad intuition to have, and we can see if we do 7 choose 2, we'll get, let's see, 7 times 6, we'll get a 28, no, 21 as our answer. And yeah, this is good, but we have to remember that this implies that we are only choosing without replacement. And that's okay, but remember that dominoes, we have the chance for doubles, because a domino can have, 1 and 1, and so on and so forth. So we need to account for those possible duplicates. In order to do that, we need to use the 7 choose 1 here. Now, I don't know if I want to, we'll go n, just to keep it the same. So we can say n choose 1 is always equal to n. So 7 choose 1, or 7 choose 1 like that is equal to 7. So we need to have 7 choose 1, actually, so we need to have 7 choose 1 plus 7 choose 2, which gives us 21 plus 7, 28, which would be the answer that we're looking for, because that accounts for the duplicates, or not the double dominoes. So this is a nice little table. This is the kind of thing that would be, perfect for perfect on your crib sheet. You have this whole thing, because not only does it have the formulas that we have been using, but more importantly, it has the dimensions that these formulas account for, either with replacement, without replacement, order matters, or order does not matter. So when we have with replacement and order matters, we know that we have sequences. That was the first thing we spoke about in this lecture. Without replacement and where order matters, now we're talking about permutations. And if we have without replacement and order doesn't matter, then we have combinations. We looked at these two in the midpoint / the last part of the lecture. Now, this point right here, where order does not matter, but we do have replacement. Where did we cover that? That was covered in this example right here with the double domino. So I would subscribe to you that it is mucho importante, very important. So example. Previous slide. Very, very important to go back and really consider this example here, because it really defines this when this occurs. And this is not very, very easy. It's complicated, and the reason why it's complicated is because you can't just like plug and chug with these kind of equations, and really, you often shouldn't do that anyways. But in these cases, or this case, or this case, you often can just use the equation. But when you have something that's a little more difficult, and again, the difficulty from this arises in the data, in the fact that the data generating process in the real world accounts for these duplicates or the double dominoes. That needs to be considered, and that needs to be also added in to the probability space, which is what we did here with the 7 choose 1. So that's it from for this lecture. The next lecture, we're going to just mostly be doing a lot of problems, and we will do some more difficult problems in class, but the next lecture will just be to kind of get your hands around how combinations and how permutations work. But more importantly, how do I take a word problem and distill down the correct mechanisms that I need to solve the probability problem, whether that's utilizing a certain equation or doing something a little more fancy like in the domino problem. So that's what we'll do for all of next lecture. And that will hopefully be very useful for you, not only on the homework, but really on the exam too, to get a good sense for how to solve these problems, a good approach. And again, read the approach to probability problems that Janine wrote, which is linked on the website. There's like several PDFs I put on the front page. And it's a really good approach to solving probability problems. Some really good information there. I highly recommend you read it. All right, we'll see you all next time.